We'll be talking a little bit more about nuclear chemistry today, and we already did a little bit with this already. You want to be able to differentiate between chemical and nuclear reactions. We've talked about this. And after the do now, you should be comfortable writing nuclear reactions with at least alpha and beta particles. We'll get into positron emission today as well as electron capture. We've already talked about the 3 types of radioactive particles. One is alpha. What are the other 2? Beta and gamma. A helium nucleus is an alpha particle. Okay? So we've already talked about that. You can write and balance the nuclear equations. And today we're going to talk a little bit about nuclear decay and nuclear decay rates probably next time. We're going to take a look at why nuclear decay occurs and what determines whether a nucleus is stable.
Oh, wait, just kidding. You can't simplify that. I was looking at the fractions for the alpha particle, and I was like, why can't you just simplify?
You don't want to simplify that.
So you wouldn't simplify it if it was an actual element?
No. All right, so we're going to talk a little bit about radioactive decay. This is where we left off. And it turns out that only a small percentage of isotopes are actually stable. 17% of all known isotopes are stable, so they don't decay spontaneously, but that means 83% are unstable and do decay. We have a name for the 2 subatomic particles found in the nucleus, and those are known as nucleons. So protons and neutrons collectively are known as nucleons. And what keeps those subatomic particles in the nucleus, and keep in mind the nucleus is very, very small, as Rutherford illustrated with his gold foil experiment. The nucleus is a very small, dense region. And so it's difficult to keep protons and neutrons there, especially protons, because what charge does a proton have? Positive. So now you've got all these positives really close together, and like charges repel. So you need something that will oppose that electrostatic repulsion. And what opposes that is a strong nuclear force. And that force acts on those subatomic particles that are very close together, keeping those protons and neutrons in the nucleus. To understand nuclear stability, you have to understand the neutron to proton ratio. And we talked about how to calculate protons, neutrons, and electrons back in chapter 2. And that's going to come back right here. It says the stability of a nucleus very much is correlated with the neutron to proton ratio. And atoms that have a neutron to proton ratio of 1 to 1 are the ones that are going to have stable nuclei. So you don't really see any radioactivity associated with the first 20 elements, although radioactive isotopes of those elements do exist. But you'll see why they exist in just a minute. If you look at a couple of elements that have atomic numbers less than or equal to 20, for example, helium, this I'm not talking about an alpha particle, this is helium. How many neutrons does helium have? 2. 4 minus 2 is? 2. 2 neutrons. How many protons? 2. Protons is always, 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 always equal to the atomic number. So this is going to have 2 protons. 2 divided by 2 is 1. So the neutron to proton ratio here is going to be 1 to 1. And when we do this division, I like to maintain to the 100th place. You'll see why in a few minutes. But it's going to be a 1 to 1 ratio. That indicates stability, and we'll take a look why in just a minute. Similarly, if you had calcium you've got 40 minus 20 is 20 neutrons, 20 protons. Neutron to proton ratio here is also 1 to 1. And that's what you find with elements that have atomic numbers less than or equal to 20. You could look at carbon, nitrogen, etc. As the atomic number increases, do the number of protons increase? Absolutely, because the atomic number, Dean, is always equal to the number of protons. So now as you have more and more protons, you have to add more and more neutrons in order to have this strong nuclear force that can balance all of that positive charge that is localized to a very small region. So what you're going to see is that the neutron to proton ratio is going to increase, and it'll reach a maximum of approximately 1.5 to 1 for the largest atoms. Once you exceed that 1.5 to 1 ratio, it becomes problematic, and that's where the nucleus is going to decay, because you'll be out of a region of stability that we will illustrate in a minute. Even with lead-207, you're getting just outside that range. We can take a look at a few elements here. For example, lead-207 is given, and again, the number after the dash is the mass number, as we talked about the other day. And let's compare that, for example, to, I don't know, pick an element. What do you want to try? No, carbon's too low. Let's try strontium. You have to be over 20. So strontium, for example, has an atomic number of 38 and a mass number of 88. All right, let's take a look at strontium first. If we subtract the two, what does that give us? Neutrons, 50 neutrons, 38 protons, and 50 over 38, 1.32 to 1. So you're still less than 1.5 to 1, which you'll see momentarily is very important in regard to neutron to proton ratio. Let's take a look at lead. If we subtract these two, we have 125 neutrons over 82 protons.
Is it always in a ratio to 1?
You're going to, yeah, because when you divide by itself, right?
Yeah.
You're basically dividing this by 38, dividing this by 38, so that it's always to 1.
Would you ever have two elements that would be, you would have to find the ratio between both
But,
of them?
yeah, and we're going to take a look at that. So here you've got a neutron to proton ratio of 1.52 to 1. So all of a sudden, you're getting outside that 1.5 to 1 region, and that's what we want to look at. So again, elements that have atomic numbers of 20 or less typically have a 1 to 1 ratio of neutrons to protons, great stability. As long as you're within 1.00 to 1 and 1.5 to 1, you're still going to be stable. But when you become greater than 1.5 to 1 or less than 1 to 1, that's where you've got instability, and that's what we're going to address. And that is a sloppy 5. You can look at this ratio graphically if you're looking at neutron to proton ratio. If you graph neutrons on the y, as shown here, and you have protons on the x, as illustrated here, what we can see is here's the neutron to proton ratio of 1 to 1. So helium would be there, and calcium would be right here. Well, it would be right here, right? 2020. Within the 1.1 to 1.5 to 1 neutron to proton ratio, this area here, is a band of stability, and most elements will be within this region or band of stability because their neutron to proton ratio is between 1 to 1 and 1.5 to 1. Once you get outside this region, for example, lead is right here, what you're going to find is that the element, the nucleus, will undergo decay, releasing radiation in the form of either an alpha particle, a beta particle, whatever it needs to do to get its neutron to proton ratio back within that band of stability. So you can learn a lot by plotting your neutron to proton ratio here and seeing whether you're within that region of stability or outside it, and we'll talk about what elements do in order to get back inside that band of stability. So again, the area on the graph where all stable nuclei are found, that's that band of stability here. Radioactive nuclei are going to be found outside the band, and they're going to undergo radioactive decay in order to gain stability. The band ends with bismuth 209, and we've already discussed that all elements with atomic numbers greater than 83 are radioactive, and now you understand why their neutron to proton ratio is not within that region anymore. The type of decay that a radioisotope will undergo depends on where it falls in this neutron to proton type grid. Is it above it? Is it below it? Because different types of radioactive emission result either in increasing proton number or increasing neutron number or decreasing it. We looked at it briefly yesterday. You may or may not recall, for example, if you emit an alpha particle, what will happen to the atomic number as compared to the original? It's going to go down. So that's going to decrease protons, increasing the neutron to proton ratio. In contrast, if you emit a beta particle, what happens to the atomic number? It's going to increase. So that'll increase protons, and think about it. If you increase protons, the ratio overall will decrease. If you decrease protons, well, in this case, you also have to think about neutrons. So if you decrease neutrons here, what will happen to the number of neutrons and the ratio? If you decrease neutrons, what happens to the ratio? It goes. If you decrease neutrons, the ratio gets smaller. If you decrease the numerator, overall it gets smaller. If you decrease protons, then the ratio gets larger. So you're just looking at the relationship there. And we'll go through a few examples, but you might actually start to see it from there. It says atoms that are above the band of stability have too many neutrons, so they'll undergo decay that'll decrease neutrons and or increase protons. Beta emission, we said, increases the number of protons, and that will lower the neutron to proton ratio. We already talked about what happens for elements that have more than 83 protons. My nose is funny. And we said that elements here are going to be radioactive, and you need to reduce both neutrons and protons there. Typically you see alpha particle emission because that has the ability to reduce both. But there are other types of common radioactive decay processes that we haven't talked about yet. One of them is positron emission. So when you have an element that lies under the band of stability, you need to up the number of neutrons or drop the number of protons. And one way to do this is to emit a positron. A positron looks just like a beta particle, except how does a positron, looking at it, differ? How does a positron differ from a beta particle, Josh? Positive one instead of negative one. If you're emitting it, it's still going to be on the right side of the equation as we talked about previously. So here it says carbon 11 emits a positron. So here's your positron here. What happens to the atomic number when you emit a positron? It decreases by 1. If you decrease proton, let's go back to this because this I know was not completely clear. When you look at this ratio, if you decrease proton, what happens to the ratio overall? It goes up. All right, so that'll get you back up within the band of stability. Another type of radioactive decay process involves, for the first time, capturing something. So you're going to have it on the left side of the equation. Electron capture is when you capture an electron, so it's going to be on the left side of the equation. And what happens to the atomic number of the product compared to the reactant? It has gone down. You've attracted or captured an electron, resulting in a decrease in atomic number. If you guys don't cut it out, I will really, really, really be majorly disappointed. So you can see that the atomic number is decreasing there. So again, if you decrease protons, the neutron to proton ratio is going to increase. And we're going to take a look at some of these examples as we go. There are a whole series of examples here that I'm going to give you time to work on. I want to do 4, 5, and 7 with you now. And I'm going to let you work on the other ones in a little bit. Let's take a look first at number 4. Number 4 says calculate the neutron to proton ratio for thorium-234. We know the element. We know the mass number. The atomic number is what? 90. How do we get neutrons? And then we're going to divide that by protons. And that's going to be 1.60. We're going to maintain to the 100th. It'll be easier to make comparisons. Is that inside or outside the band of stability? Outside, okay. And you can go around and it's in the second drawer and just take out for anyone who needs, please. No, not that one, the plastic thing. The second drawer, middle drawer. There you go. Questions on the neutron to proton ratio. And we've established that it is outside the band of stability. All right, so So that's very straightforward. Let's take a look at 5. 5 is more similar to what you will see on your quiz, not your test. Your quiz right now is slated for Thursday next week. On number 5, it says write a balanced nuclear equation for the beta decay of uranium-235. I'm putting that on the screen. You know how to write this. It is easier than what you saw on the Do Now. Take a minute to try and write a balanced nuclear equation. Were you successful in writing the balanced nuclear equation? There's my balanced nuclear equation. Okay? Alright, and the second part says what happens to the neutron to proton ratio? Does it increase, decrease, or remain the same? So how are we going to figure out neutron to proton ratios for these two elements?
Use 235 over 92 for uranium.
No. That's a common mistake kids make. How do you find neutrons?
Oh, he's a tragic.
Right, and that's it. Be careful. It's better to make the mistake now. So you've got 143 neutrons to 92 protons. And that's 1.55 to 1 for neutron to proton ratio. And how would we get neptunium? So what happens to the ratio? The ratio decreases because 1.53 is less than 1.55. Or you could indicate that the ratio decreases with an increase in the number of protons, because the numerator is the same, the denominator, well actually the numerator has changed, but the denominator has increased. You actually have a decrease and an increase, which results in a decrease overall in either instance. Okay? So very straightforward, and that was number 5. And then number 7 is one of these new types of decay, but really pretty straightforward. In number 7, what we're looking at, it says nitrogen 13 captures an electron. How do we write nitrogen 13? Okay. Now it captures the electron, so the electron has to go on the left side of the equation. It looks like a beta, but you just write E for electron. And what does it make? You've got 7 plus -1 is 6, 13, and that would be carbon. And this one also asks if the if the neutron to proton ratio now is within the band of stability. So you want to see whether it increases, decreases, and what happens to it. So this would be 13 minus 7 is 6 over 7. This would be 13 minus 6 is 7 over 6. And you can tell that's going to be within the band, and that clearly wasn't because it's less than 1. So this was 0.857 to 1. As such. So clearly the neutron to proton ratio did what? It increased because 1.17 is greater than 0.856. So capturing an electron has the effect of increasing the neutron to proton ratio, and this now is within the band of stability. So at this point, hopefully you're starting to get a feel for neutron to proton ratio, the importance of neutron to proton ratio, understanding beta, alpha, positron, and electron capture. So these were emission processes on the right side of the equation. This is capture on the left. And the effect that each of these types of radioactive decay has on generating a substance that differs from what you started with. Remember, we said nuclear reactions were very, very different in regard to generating atoms that are not listed as reactants. So there's some key differences, and that was one of our objectives to understand. In regard to your classwork, I will tell you which ones you can do at this point. And you already have your classwork. You can do 1 through 7 on the front, and you can do 10 through 15 on the back. And in the next lesson, we'll be addressing radioactive decay rates, which is very simple. You'll be strong there. And we'll talk briefly about fission and fusion, but really just the decay rates. That'll be a very short lesson that we'll look to do after your test. Questions on nuclear? Yes?
Is our quiz going to have, like, what the Currys did?
No. On your quiz actually is going to be nuclear and the very beginnings of gas laws, just like the easy stuff in gas laws. But of the nuclear component, you'll have a question where you write a nuclear reaction and you analyze it for neutron to proton ratio. And one of the questions will be on decay rates, which we'll get into next time. And then quite a bit of the quiz is on gas laws, which is very mathy, and you guys will be extremely strong with. All right? In regard to your test, which is our next block period, your test covers stoichiometry only, and we can discuss that. Questions here?
Are we gonna do clickers before the test?
I'll get to the test set. Questions on nuclear? You're good with nuclear? The lesson was straightforward? Okay.